I'm not a finance person, so actually, I was happy that I can still understand my mortgage. So I'm here only to talk more about technology, that I understand at least a little. And I want to talk about energy. And energy, you probably, a joule. There are some people from the United States, so they still count in firms. A kilowatt hour, you probably all have seen maybe on your electricity bill. And coming back to the question raised earlier, many of us still see the energy bill as an act of God. And that's why we don't manage it. We don't see energy as a manageable cost factor. So we just pay these things. BTUs, all the British thermal units, only still the United States use BTUs. Megajoule, you probably gigajoule, but have you heard about a kilowatt? A negajoule. You probably haven't. And those actually are the most interesting ones because we don't have to pay for them. And actually, energy is incorporated in all the prices. So if prices go up, energy prices go up, everything will go up. And that is actually the core of the thing we use, because the future is about the energy that we do not use. And buildings is actually an extremely important energy user today. Basically, it is the largest energy user in the world if you count the electricity that is used by appliances in those buildings and the computers, etc., that we all use. Together, they use about depending on what country we are in, with 25 and 40% of all the energy. Again, also counting if you count the electricity that we use indirectly. Buildings are therefore responsible for 30 to 40% of all the carbon dioxide emissions in the world. And buildings are going to last for a long time. So the building that we build today will be there over the next 50 years. And it's going to affect energy use over the next 50 years. And that is why it's so important, the stuff that you are doing, because we have to change this trend, because we're doing it completely wrong. Talking about the life cycle of a building, basically in all stages of the life cycle we use energy, we do emit CO2, but also we use some materials. And this is a typical life cycle. We extract limestone to make cement. And nearby we have the only clinker plant in the Netherlands. It's just a few kilometers from here. You can see the stack. And when we make cement, we use a lot of energy. We also use limestone, and limestone is converted to lime in the making of cement. And for every ton of limestone that we convert, we produce about 500 kilograms of CO2. So every ton of cement that you use is responsible for about a ton of CO2 if you include energy use. Still, most of our energy that we use is during the lifetime of the building. And that's because we build buildings in a dumb way. And so actually the flow, where you see it here, and actually when we do in the end, in the final stage of life, we also generate some emissions, but really trying to reduce lifetime energy use over the life of the building is key. And I first want to take you a little bit through some of the IPCC results. I've been an IPCC author, and show you the importance of energy efficiency and then go back to the buildings. So what we have seen basically between 1970 and 2004, global greenhouse gas emissions have been increasing rapidly, about 70%. And of all the greenhouse gases, CO2 is the most important one, and that is directly related to how we use energy. So the lower graph shows you CO2 from fossil fuel use, and you see the size. And the other basically CO2 from decay, or it's the other greenhouse gases under the Kyoto Protocol. If we look to the future, basically we have to stabilize emissions in the atmosphere. There are now, if you talk about discussions in the negotiations, we're talking about two scenarios. One is called the 450 ppm scenario. That is basically, if you go back to the UNFCCC climate treaty, if we do not want to have irrevocable damage to our climate system, that is actually the maximum. Although some scientists now say we have to go back to 350 ppm, parts per million of CO2 concentration in the atmosphere, to really make sure that we don't have any problems. But there are some people already saying that we cannot make 450 ppm because actually we are too slow in implementing the changes. So they think about a 550 ppm scenario. And today we are at 380 ppm. And so, and we already see the changes happening in our climate system, although we cannot really fingerprint it due to climate change, yet it's already happening. But what's important from this graph is that if we go to a 450 ppm scenario or a 550 ppm scenario, energy efficiency has to do the bulk in reducing emissions. And so basically what James told us this morning is true. Renewables are sexy. nuclear power may be not sexy anymore since a week or two, but it is about energy efficiency. It's about a lot of small things we need to do, and together they add up to a lot. And this is true. This is from the International Energy Agency, the World Energy Outlook, but this thing is shown by many studies. For all countries in the world, we get to the same results. Yet, we see that we are not doing enough on energy efficiency. Also, the IPCC showed that. It showed basically that there is emission reduction potential in all sectors. These are the different sectors from basically how the IPCC looks at the world. But the key message here is the biggest potential is in buildings. So it's found in all sectors. And the other part is, this is divided in 3 columns. It's expressed as mitigation costs, so dollars per ton of CO2 mitigated. And the left-hand column in each of the sectors is $20 per ton of CO2. Currently, the price within the emission trading system is about 20 euros per ton of CO2. So that is about the current price that you would pay today. And we already see that the large chunk of the potential is already affordable at that stage using social discount rates. So maybe not what a typical investor would use as payback, but from a social perspective, these investments are already valuable. And we see, if we go up to higher carbon prices, the total potential increases only small, whereas for the other sectors, this is more importantly. This is a so-called conservation supply curve. This is basically a typical demand-supply curve from economics. This is done for the US by McKinsey. And it shows every block is an action, a mitigation action to reduce CO2 emissions in the United States. And the important thing here is that you see the orange ones, those are in buildings. And the key message here is buildings are, and therefore also in the US, an important factor to reduce emissions. But also they are, again, most of the orange is in the cost-effective part. So again, buildings are not only offering a big potential, they are also offering the largest cost-effective potential. And this is the similar graph we've done for the Netherlands. We also made supply curves. And here, again, half of the energy efficiency improvement savings that we can find in the Netherlands are building related. Either the appliances, the lighting, or the building itself. And again, these are the most cost-effective ones. So now turning to buildings. Where is most of the energy going? In the north climates here, we spend most of our energy on heating. And lighting and appliances are also important, and increasingly important, because especially appliances, we have a huge amount of appliances that use power all the time without doing anything for us. 10% of all your electricity use at home is now going to standby. It's going to your microwave, just running the clock. It's going to the set-top box or your television, just sitting there. And yet we pay for 10% of our electricity budget right away. But space heating is still like half of the energy use, half of the budget where we spend our energy in buildings. And this is a trend of space heating in kilojoules per square meter and corrected per heating degree day. So this takes climate into account. And what we see here are tremendous differences in energy use per square meter. We see that Japan is on the lower end, slowly increasing because they used to have very localized heating, basically a stove underneath your feet, is traditional Japanese heating, and now they're moving also to more centralized space heating like we have here in Europe. But we also see some European and the US where are large energy uses per square meter. So there's a big gap between the two. This is important. That means there's potential for improvement. But secondly, also, there's another interesting thing here, is that's the blue and the red dot. That is China. The red dot is energy use by the rural population for heating in China. It is extremely low. It's cold in a Chinese home in a rural area in the winter. The blue dot is the average of an urban home in China. And now think about urbanization happening in China. This is a disturbing trend. Some of the apartments in Beijing, there are 200 square meters. I mean, they're bigger than the apartment here, than we have here. And that is, that is a trend that's happening. So we can see actually the energy use in China, now 70% of energy use in China is in industry. We see the share of buildings starting to increase. That is worrying. So what can we do about it? Well, typically, we lose all the heat that we put in the building, because otherwise we don't have to enter heat all the time. And this is the typical losses. So 10% for the windows, 35% for the walls, 50% for the floors, and all these things we can control. We tend not to control them, and we can either, so what can we do about it? Well, another thing about talking about dumb and smart, typically the energy bill that you pay is about enthalpy. So it's the first law of thermodynamics that you pay for. But the real efficiency of our system is defined by two thermodynamic laws. The second one, entropy, which is hard to explain, but basically it works. It's the amount of work that you can get out of a piece of energy. That defines the ultimate efficiency. How far can we go? And we also, when you buy a new heater for your home, they tell you it's 97% efficient. I have one at home, which, funny enough, has an efficiency of 107%. How it can happen, that's another discussion about thermodynamics, which I won't bother you with. But in fact, if you look at the second law of thermodynamics, the efficiency of heating a home, an efficient home heater system, is less than 4%. 96% of the quality of the energy carrier we waste, because we tend to heat a home to 19, 20 degrees Celsius. And there are many other things that we do in a dumb way. I mean, how many of you have at home have an electric doorbell? Probably everybody. An electric doorbell uses power all the time because a transformer pulls power from the grid. Yet, unless you live near Jehovah's Witnesses, your bell is only used by 1 hour a year. So 8,769 hours a year, the thing is pulling power, not doing anything for you, yet we accept it. So we accept more than 99% waste. Is there any industrial process where you would accept that you produce 99% waste and 1% useful product? Except for airplane industry, that is not a very good way to run a business. And there are more examples like that. Incandescent lamp. How many of you still have incandescent lamps? I'll be honest, I have some too. Efficiency is 5% of the lamp itself. 95% is waste heat. And if we take the whole system into account, then the efficiency comes down to about 2%. Well, that's 98% loss. So we are not very smart. Although we tend to think that we are smart, and this is actually taking away some from one of the next speakers. This is the Deutsche Bank building in Hanover, which is actually a pretty smart design. Not anymore. Oh, I thought it was. Sorry. I thought it, okay, anyway. You can correct me. But the key thing is that we have to think smartly about building as a system. And we now think about the components. Actually, when the construction is done of a building, it is done by components. It's outsourced. I mean, we have large construction companies, but in the end, it's an electrician. If it's a single-owned company, family-owned company that puts electricity in your home. And that's how the whole system works. But nobody really looks at the design is maybe as a system, but the implementation of a building is not a system. So when it's actually built, many errors are being made. And also then again, when the building is commissioned, a lot of errors are made. So the example of the building in Birmingham this morning is a key example of where things go wrong. And that is very usual, I can attest to that. I have worked for a consulting company where we had energy meters in a lot of buildings, and we could see when the maintenance guy is coming in. Energy use would go up. So whenever the maintenance guy would have come in, we should somebody over there to turn back the settings to the right setting. 30% energy savings. And then there's, of course, a lot of new materials being developed, new building construction materials being developed. So looking at vacuum insulation, triple glazing, which is very useful, of course, in Scandinavia, but not yet here. People are working on heat change, materials that we can store in a phase change. So actually some people in California have developed a wall carpet that can absorb heat during the day and then send it off in the room again at night. And because that's basically the question. Often during the day we have too much energy, and during the night we have a shortage. And there are many other technologies being developed. One of them, of course, when you think about a system again, is the passive home. which is, I mean, in Germany, a big trend. Germany, Austria, Switzerland are leaders in that field. Germany now builds like 15,000 homes to passive home standards. And this graph shows you the development over time of the energy use in a typical house in Germany. And the red part of the bar, that is space heating. And a passive home basically does literally hardly need any space heating anymore. So it has come down over time. And this is all existing technology. We can do it today. We just decide not to do it. The government doesn't put the right standards in place. The Netherlands has slowly improved the standards, but it's slowly, and the homes that we build today, they're still using a lot of energy to be heated, although they're much better than homes from 10 years ago. But those homes are going to be there over the next 50 years. And this is more information that I won't go through it, but I mean, there's been many different nice examples of passive homes. They don't need to be ugly. They're easy to live in. They only need they don't need heating in extreme weather events. And remember, I mean, each of us, we all generate about 100 watts of energy continuously. I mean, we're also tremendously inefficient. Especially men. We men generate a lot of waste heat. So if you have a cold home, just get some men in there and the thing will heat up. Are energy efficient buildings expensive? No. No, I think the examples we heard this morning show that it's not expensive. These are some studies from the US, from Manhattan, showed there's a small first cost increase. But again, it's about life cycle costing. Most of the costs are made during the use of the building. A study from the US, from California, showed almost negligible cost increase. And if you, I mean, a more statistical study about 600 projects in the US found basically no statistically significant difference in first cost. So we can do it cheaply, yet we don't. And therefore, I want to end with, well, not yet, I have one final slide after this one. Basically, I think on technology, it is not rocket science we're talking about. It's about integrating, and it's looking at the building as a system and operating the building as a system. And combining, from that perspective, combining the right technology. And in the meanwhile, we're developing more efficient technology. So we can still go further. Technology certainly has a role, but we can do it today. But the key to success is integration. And for that, we need help. We need help from the market. We need help from government to set the right policies, set the right standards. And we need help from people to realize that we spend a lot of money on operating a building. And finally, also, it's about innovation, but also training about innovative technologies. Because that's often where it goes wrong in the construction sector. People are not trained to use innovative technologies. We have had a neighborhood in Apeldoorn, which is a city, the 10th largest city in the Netherlands, about 15, 20 years ago. And they were going to build solar water heaters in the roofs. And everything you can imagine has gone wrong in that project. First of all, the neighborhood was such a way designed that half of the homes did not have a roof on the south side. That is where we get the sun in the Netherlands. So, first problem. Then, during the building construction site, we were walking through the street, and there's like a big hole where you put the solar water heater at that time with those systems which are used at that time. You could see them on both sides of the street. You could see the hole. So that means half of the homes, somebody had put the hole on the north side. Not the right place when you capture sunlight in the Netherlands. Then a lot of the systems were wrongly connected. So they were pumping hot water from the backup boiler to the solar water heater to be cooled down and then go into the system. Everything went wrong. And it's just basically people were not trained to work with innovative technologies. And just to give you an example, it is not rocket science, and that we can learn a lot. And maybe we have to go back to some roots. I want to use this one key example from the Haeinsa temple in South Korea. It's a Buddhist temple. It's a UNESCO World Heritage Site in the mountains of South Korea. It is also the depository of the wooden Tripitaka, which is kind of for the Koreans, the Buddhist Bible. It is in the pictures below, that's the wooden panels, and they were stored in an open building. And in the 1960s, because it became a UNESCO World Heritage Site, the government of Korea found we have to really we have to store this for future generations. So they built a new building, air-conditioned building, and they thought it was state of the art at the time. And they put the wooden Tripitaka panels in there. Within weeks, mold was forming on them because they couldn't really control it. Whereas the original building, so within weeks it was moved back to the original building. The original building was built with passive ventilation. So it was built on the mountainside that the wind will blow through it. It was built in such a way that it controlled temperature very well. Even with the extreme temperature differences in the mountains of South Korea, the temperature differential within that building was only a few degrees, up to 5 degrees. And they used a lime on the floor to control the insects, so the insects were not eating away the wood. So in the end, the monks, 1,000 years ago, were smarter than the people in the 1960s. And there are many examples where we can learn from the past. I mean, there's a large group at Lawrence Berkeley National Laboratory that looks at urban heat island effect. The first thing they did to study this is to go to a town in the south of Italy, which is completely painted white. Because of that, they figured out 600-700 years ago, by painting the town white, we control the urban environment better. And with that, I want to thank you for your attention.